So welcome back. Thanks for showing up to get some candy or showing up on Zoom, however you want to do it. Today is going to be the analog of right before you go on vacation or go on a big trip and you try to eat everything that's left in your fridge. So dinner would be like some of this and some of this and some of this and whatever's in there. That's what today's going to be. It's going to be like a potpourri of whatever we haven't talked about in Unit 6. And maybe some in Unit 5, I think, too. So let's see. Next items on your to-do list would be formative assessment 5. Are we up to 5? That sound right? Whatever's due next. You can just see an icon. It's a story problem, so that should hopefully be more entertaining. I'll spend lots of time on that on Tuesday. And your next homework is also available, and it is over piecewise models. That will be due the following Monday, so the 18th, I think. And as I warned you last time, this one will be the most complex, I expect, of the semester, because it's combining piecewise models with quadratic models. Like, oh yeah, the piecewise slopes get to be quadraticized, if that's a word. So it will be a little bit more intensive in terms of figuring out what the right code and what interpretations would be. But as usual, we are here to help, so don't be shy. Let's see. Unit 7 is going to introduce predictors. We're almost ready to do that. It's almost Thanksgiving and we're almost getting to predictors. But time is hard. Time is a major design characteristic that we have to pay a lot of attention to. Otherwise, everything we do after this is not going to make a lot of sense. So, all right, let's see. I think I want to pick up on first leftover, as it were. Slide 10 I never did. I realized that. It's way back at the beginning. So we're talking about absolute tests of fit. So when you are using regular flavor maximum likelihood, which would happen if you have a large enough sample size, or you're using software that doesn't have REML instead, like an SEM type of program, then you can compare any kind of model you want. So you can test differences among fixed effects, differences in random effects, or residual correlations, both at once. The rules are fine. So testing absolute model fit is relatively straightforward in ML because you have this likelihood ratio test machinery by which you can throw at any problem. So in terms of the model for the means, just to recap, the right answer, so to speak, if you have balanced data, is saturated means, which is treating time as a discrete predictor. So you would have as many fixed effects as you have occasions. So then the question is, relative to that as the rightest answer, how well do your fixed slopes related to time do in reproducing those means? So we looked at, as an example, in 6D for log time. Let me go back a few slides here for that, put it into context. Almost. There we go. So we looked at this last time, but this is what I'm talking about. In this example, we have 6 occasions. So if I have a fixed intercept and a fixed slope of log transform time, so that creates this sort of bendy exponential-like curve, that's the reason we would do that, then I have potentially 4 degrees of freedom left over. So do the two parameters do a good enough job at capturing the 6 means? I can test that when I'm using REML estimation by adding these binary contrasts. So these are going to fill in any discrepancy between the trajectory that is created by the fixed effects and what the actual trajectory of the means would be. And in this case, it looked like the F-test for combining those things was non-significant, meaning that my model did a good enough job. Now, what happens in unbalanced data? Do you think I can do this? If everyone's on a different measurement schedule and different occasions potentially across people? Yeah, I don't think so. I think the best you could do in that situation is round time to do something like this, but that's kind of icky. I wouldn't round time and put it in a model because that's just introducing measurement error. You usually don't want to do that on purpose. So I had never really thought about this, but then I read this idea in this book. There's a link to it, and I thought, hey, I'm going to steal that. So that's what we're doing with that. So we can't use likelihood ratio tests, we can use multivariate Wald tests, meaning lumping slopes together and asking for a chi-square if you have a large enough sample, but I don't usually live in that world, so we can ask for an F instead. So you know this idea by many different names. So for instance, when you treat time as categorical and fit a saturated means model, you get an F test for that, right? For whether there's occasion mean differences. That's this kind. You're lumping the slopes together to see if there are mean differences over time. That's a multivariate Wald test. If you do a hierarchical model where you start with predictors in one block and then you add another block of predictors and you look at the change in the R-square and the F test for that, that's a multivariate Wald test. So this is a very general idea that shows up in a lot of specific instances, so I'm borrowing that technology to do this. On the variance side, though, we do need to have likelihood ratio tests for that. But then the trick is, given that we're using Dremel estimation, we have to keep the fixed effects the same. So in the example, so this is the testing the means model. Testing the variance model then is done by fitting a comparison model in which I have the same fixed effects. So I'm keeping my fixed intercept and fixed slope of log time, but I'm changing the model for the variance to be an unstructured R matrix. And note the no constant here. Do you remember what that does? What does Stata think the constant is? Intercept. Yeah, so what this one is doing is shutting off the default random intercept that would be here. So then everything is back in the R matrix as the rightest answer. So then we can compare against our prior model that had a random linear slope for log time. There we go. And that's a likelihood ratio test. So that one was significant, meaning it didn't do a good enough job. So in SEM or in maximum likelihood, you could test both of these things at the same time, theoretically, but I don't think that's necessarily as useful, because if it fits, like you could be overlooking little pockets of misfit, and if it doesn't fit, then you're not really sure where the problem is, if it's on the mean side with the fixed effects or the random effect side with the variances. Okay, so any questions about those ideas? Cheers, I'm back to caffeine. It's fine.
I have a question about that test, the multivariate Wald test.
Okay.
Could we change our estimation method to ML, estimate both models, and then perform a regular likelihood ratio test?
You could, but I would be concerned that in smaller samples, the random effect variances would be too small, and so the test is not reflecting the same model that you're hoping to interpret.
Okay.
So I've seen people do that, and I've done that before, but I don't think it's as useful as targeting each side of the model in this more specific way.
Great. And I have another question about balance time.
Yes, balance time.
Yes, when we have unbalanced time, you mean that the meaning of the unit of time is different, or do you mean that the labels we are using to represent time in the model are different?
I mean neither of those, actually.
Oh, okay. Yeah.
I'm not sure what you mean by labels. Can you expand on that?
The numbers that we have. So let's say that we have 1 week, 2 weeks, 3 weeks.
Okay.
Right?
1 week,
So,
2 week, 3 weeks. I'm not just echoing you. I'm trying to make sure the recording
yeah,
gets
of
the
course.
words.
In that case, we know that the meaning of one unit is different between those three occasions. Between occasion 1 and 2 is 1 week, but then it's 2 weeks, and then it's 3 weeks.
Oh, okay. So there's 1
However-
week in between, 2 weeks in between, 3 weeks
Yes.
in between. Yes.
Exactly.
Yes.
However, in the model, we could use labels 1, 2, 3. So that's my question. My question is related to what's the meaning of unbalance? Is related to the meaning of the unit of time in the model, or is related to the labels we use to represent time?
Okay. So the question is, what do I mean by unbalance? Do I mean that there are unequal intervals between occasions?
Exactly, yeah.
Okay. What do you think? I'll throw this to the class.
unbalanced, you could label them like 1.5, 2.3, or whatever, right?
Yeah, you would need a time variable that keeps track of how long it's been. So if the first occasion is 0, and then it's 2 weeks later, then the next one would be 2, and then the next occasion would be 5 if it's 3 in between, right? So you would need to account for that in the model, otherwise it wouldn't make sense. There's another, that is, I would call that not unbalanced. The word I would use for that is unequal intervals. And there's no problem with having data that aren't equal interval. It just restricts, like, you can't fit a Topolitz model. Okay, so what? That's not really a real restriction. In general, I think in designing longitudinal studies, you want to have as many observations as possible during the periods in which you're likely to show the most change. So for instance, if you're doing like a weight loss study and people initially lose a lot of weight, thinking back to the Biggest Loser television show I used to watch, they always lost like 20 pounds the first week. And then eventually your weight loss kind of levels off because you can't keep exercising and starving yourself forever. Your body does not like that. So if I were trying to track someone's progress, I'd probably put more occasions at the beginning and then fewer at the end where I would expect less action. So I would deliberately make it unequal so that I can have the most sensitive change. They don't have to be equal. Now, what do I mean by the word unbalanced? And it's a good thing to say it that way because not everybody uses words in the same way. What do I mean when I say unbalanced time?
Participants have different number of occasions.
Different number of occasions, and I would say that's more like incomplete versus complete. Like if you intended them to have 4 and they only have 3, I would probably not use the label unbalanced, I'd use the label incomplete. Kezia.
There isn't the exact same amount of time in between occasions?
That one, so the exact same amount of time in between is equal interval or not. That was the example that Vladimir gave, actually. Like if there's 1 between, 2 between, 3 between, that's unequal interval, but it's still balanced, actually. If everybody is, what's the key idea here? They're all on the same schedule. So the cortisol example, for instance, let me find that slide. I think that's a great example of real life unbalanced time. So the x-axis for time in this picture is waking up, 30 minutes later, lunchtime and bedtime. And as we've discussed at length, those numbers are not going to be the same for most people. So if someone gave you 3 samples out of 4, that's incomplete. But if some people woke up at 6 a.m. and some people woke up at 10 a.m., that's unbalanced. And
Doesn't it depend somewhat on how you're defining it, like what the, because I remember that we talked about at one point, like students on a semester. So like if you have like a semester and like this timing of students like within that. But we had an example where they were on a similar schedule. Like you could say that wake plus 30 minutes lunch bed is a common schedule, but it depends like when you dig in underneath, like how obviously for a lot of these we're taking time very seriously in the sense of like we want specifics. So
yes.
like 30 minutes after is a very specific amount. But if you're looking at time like over years, then that is like a less specific kind of time. And so then how are we going to define balanced versus unbalanced? Like if our time is changing.
Yes, so great points. Let me see if I can recapture those. So in some contexts, balance will matter more than others, I think. So you could use an example of like if I measure kids in the fall, in the winter, and the spring, I would want to know exactly when those were. Because if somebody was measured like 2 months later and someone else was measured 4 months later, the kid who's measured 4 months later has more of an opportunity to show change. But it's artifactual because it's still change per month as what you're trying to estimate. So you want to know exactly how much time has passed. And so to your point about if you have a study that's, let's say we're measuring older adults, a lot of my examples have older adult data, and you measure them once a year. There's not a lot of change that would be differentially informed if I did an observation 1 week versus 2 weeks later, right? They're still 85 years old. 2 weeks is probably not going to make a difference. But if I'm studying babies, like making babies freak out on purpose so I can watch them react. It was a real study. I'm not making this up. Then I would want to know, is this child 3 months old or 4 months old? Like even week to week, like what they're able to do is very different. So it depends, right? Like it depends on your context, I think, how much unbalance is actually going to matter. And there are ways to answer that question empirically. In the second example of chapter 10 in my book, that is the study that is using a measurement burst design. So what we're analyzing in example 6D is one observation of that design, where you have 6 observations within a 2-week period, and then you repeat that set of observations 6 months apart. Well, it wasn't exactly 6 months apart, as you might imagine, because these are people that don't exactly follow every instruction. Like, you need to come in on Monday. Like, oh, well, no, I have bridge on Monday, and Tuesday I go bowling, and Wednesday I've got bingo, but I've got Friday open. Will that work for you? Like, these are older adults, right? They're retired. They're living their best life. I just gave you my mother's schedule, actually, although she goes bowling on like Wednesday, she plays cards on Thursdays, she has a singing group on Tuesdays. No, this is hilarious. She's part of a singing group like the Swinging Seniors or something, like it has some catchy name to it, where they go perform at nursing homes. But everyone in her singing group is like 70 or older. And so they put on costumes and put on shows, and like they're living their best life. So I'd like to do that when I'm 70. I think that sounds like fun. But anyway, back to my point. Now I'm realizing why I don't allow myself to have caffeine in the afternoon. So I need to move that away before I start going too far off the reservation. So these people were not measured at exactly 6 months intervals, and we pretended like they were. So what I did was create an offset predictor for how far off from 6 months their observation actually was. And then you can test fixed effects of that to see if that matters. And I would do the same thing, by the way, in educational contexts where you have children who are organized into grades, but they're children of different ages. So like in my son's class, there could be anywhere from, say, an 8-year-old who might have skipped a grade up to like a 10 or 11-year-old, all within the 4th grade. Well, do you think an 8-year-old and an 11-year-old are the same? No, not just because they're in the 4th grade doesn't make them the same, especially if you start looking at outcomes that aren't just academic. Well, in that case, what I would want to do is not put in age and grade, because they're going to be so highly correlated that it would be difficult to interpret their effects. What I would do instead is add an age offset. So like if the expected age in 4th grade is 9, how different are you from that? So then you can look at the effect of being relatively older than your grade and the effect of being relatively younger, which has differential meaning than just being 8 versus 9 versus 10. Question? And then I'll get to the Zoom question here.
Yeah, so kind of in that same vein, so working in a clinic setting, we have people scheduled for like certain blocks of time, so like 3 weeks at a time. But the amount of stuff we might actually accomplish with each patient in those blocks varies. Like, so for some people, we might have 50 sessions worth of work, and others it might be, 150 or whatever. So in that case, even though they're all there for 3 weeks, it's probably more important, right, to track it at that session level as opposed to like the 3 weeks is kind of the time predicting time. I'm not gonna, that time.
Yes, so if you're having a child get services for a 3-week period and some people end up getting more services during that, yeah, absolutely, I would think that at least is an empirical question, whether it matters. It seems like it would, though.
Okay, yeah.
And it would also probably reflect, I'm guessing that people are not randomly assigned to getting only 5 or only 10 or only 30.
Right.
So how many they have is probably related to the behavior that you're trying to help them with.
Yeah.
So for that reason too, it could potentially end up backfiring in that like it looks like more sessions is more hurtful, but it could be because the kids who need more help need more sessions, so they're not the same.
That's, yes. More on that later. but
More on
yes.
that later, okay. Hillary, did I answer your question all the way, or did I get too far off track? Okay, cool. Question in the chat here, if you collect data in waves, is time balanced? Let's say a wave is a month, so if someone fills out the measures on January 2nd versus January 28th, that doesn't matter, right? Because the data was all from wave 1, so it would be balanced. I think it matters sometimes. I'm not trying to be cagey, I'm trying to be realistic. It depends on the time scale of what you're tracking and how much change would happen between January 2nd versus 28th. It's an empirical question at the very least. So my default position is that you want time to be as exact as possible in your data set. I think you use those words too. Like literally dates and times stored with your data so that you can compute actual distances. And by the way, all software has built-in date stuff. Like you can plug in dates and figure out how different they are, and it keeps track of leap years and which months have 31 days, and like all that stuff is baked in. You don't have to do that. So working with dates is ideal.
I just went down the rabbit hole of the dates and data, so.
See,
I have an example about, we were trying to kind of impose a balanced time in one of the studies that we're working on, where we're essentially tracking a comprehensive support program for first generation, racially minoritized, low-income students. And we essentially selected weeks that we felt were meaningful and then measured a whole bunch of psychosocial outcomes. And we intentionally only kept the data collection open for a week and turned it off so that, like, if people wanted to come back a month later and take it, they could.
Mm-hmm. Yeah, no, that makes sense. So you're saying it's balanced within this interval, but then you controlled the interval to make sure that it didn't stretch too far. Because, yeah, at what point does wave 1 become wave 2? It's tricky. This is where, by the way, the idea of unbalanced time is the biggest difference between fitting these models as multi-level models versus structural equation models. That was one of the topics that I wanted to hit on today as well. So, Zoomers are good? All right. Other thoughts, questions, examples? This is good. I like the talking. This is way more fun. Do we need to send the candy bowl around again?
Sure.
Yeah, okay. Somebody please send the candy bowl around again. I got extras for the next class, so. All right. So nothing more on that point? So unbalanced time is not the same as incomplete data is not the same as unequal intervals. Those are 3 different concepts. Balance refers to everyone being on the same schedule or not. Equal interval refers to the distances between occasions being the same or not. And incomplete means you have all the intended observations or not. 3 different things. Yes?
Can you say, like, the unequal interval situation is kind of like having ordinal, time as an ordinal variable? Because, like, the occasions are ranked in order consecutively, but we don't have the same amount of distance between them.
Okay, so the question was, can you think of unequal intervals as ordinal instead? Like so in Vladimir's example, if I had 1 week apart and then 2 weeks apart, 3 weeks apart, I could call that time 1, 2, 3, but that doesn't make sense because it is only ordinal at that point. But it doesn't have to be. Like, it doesn't make sense, I think, to treat it as ordinal when you have the information about how far they actually are apart. And why that's a problem is, think about if you fit a slope through time 1, 2, 3 in that example. The slope is supposed to be the change in the outcome per unit time. Well, what's a unit? Is it a 1 week a unit? Is 2 weeks a unit? Or is 3 weeks a unit? And the answer is yes. Yes, it is. What do you do with that? So in ordinal data, you don't want to treat it as interval because you're assuming that the effect of going from 1 to 2 is the same as 2 to 3 is the same as 3 to 4. And that's not likely to be the case, which is why we have different models for ordinal outcomes than we do for standard conditionally normal outcomes. All right. Yeah, I just put the beach back up because I figured let's eat candy and look at the beach. You know. Mindfully, though. Mindfully. Whatever the hell that means. I don't know. I have a friend who does mindfulness training. I should ask her. All right, so we talked about fits. Let me finish the end of this thing here. So the end of example 60, we worked our way through linear versions of log time and then fixed quadratic versions of log time. Adding the fixed quadratic slope helped. So it fits the means a little bit better. Here are predicted outcomes and predicted slopes. So remember the deal with squared things, quadratics? if you're creating a predicted outcome, what do you do to time in the prediction? Square it. If I'm creating predicted slopes, what do I do to time in the prediction? Times 2. Yep, just remember that rule and then you'll be good to go. So this is log time, this is log time squared. Down here, I have log time times 1 because that's the start of how I make a linear slope for any occasion, and then the value that I fill in here is times 2 for log time, because twice the quadratic is how the linear slope changes per unit time. All right, so here are the predicted intercepts and predicted linear slopes. So you can see the slope is becoming less negative over time, but not in an equal interval fashion. It's quadratic now. And let's see, we looked at this, green line versus yellow line. Green does a little bit better, so it's significant, but it only accounted for another 1% of the residual variance, so not super exciting. Fixed quadratic random linear, that's the same R code, so that in the contest 1Ds, we have time and time squared for the fixed predicted outcomes, and we have times 2 for the predicted slopes. Random quadratic version. How many random effects are in this model right here? How many random effects? Okay, so I'm seeing 2 different numbers. Let me ask the question, how many random effect variances specifically? 3. And then folks who said 6, what were you also counting? Covariances, yes, you're both right. So what is the dimensions of the G matrix in this model then? Where the random effect variances and covariances live.
Can you repeat the question?
Yep, what are the dimensions of the G matrix?
6 by 6.
We got 3 by 3 or 6 by 6? What's G again? No vocabulary drill. Is G level 2 stuff or level 1 stuff? 2. It is the individual differences matrix, level 2. So what are the dimensions of it then if I have 3 random effect variances and 3 random effect covariances? 3 by 3, yep. So you can actually print that in software. I don't usually bother because the same information is tabled like this. This is stata output, and then this is the G matrix for stata. So it has it in a different order based on other programs, but you can see the same thing. So these are the correlations among the random effects instead. Now the 6 by 6 people, what question were you answering? V. Yeah. So what's R again? We forgot that one. Level 1? What are its dimensions if I have 6 occasions? It's 6 by 6 for each person. Now, why didn't I bother to show any R matrix in the output, do you think?
We're assuming it's independent.
That's right. It would not be an interesting matrix because you would have this residual variance on the diagonal and you'd have zeros or holes everywhere else. Now, does it have to be that way? No, you can test whether the residual variances want to differ over time. You can test whether there's some kind of residual correlation over time. The variances one is tricky though. That one is, if you allow heterogeneous residual variances, that's going to compete with what the random slope variances are trying to do because they create heterogeneity of variance too. So they're redundant to some extent. So the R matrix then would just have this on the diagonal and zeros in everywhere else for this model. Yes?
We've used the word redundant a number of times. When I hear that word, should I interpret it to mean that if I ran like a model comparison of like, let's say an ACS model that's heterogeneous with like a random slopes model, most likely they would not be significantly different from one another. So redundant means like not significantly different.
So the question was, do I mean not significantly different in terms of when I'm saying redundant? No. I mean that they're each different ways of trying to recreate the patterns in the data. So if you just allow the residual variances to be different over time, not going to say the H words, they're too long, different over time, then that would allow, where's a V matrix here? A V matrix that has different numbers on this diagonal. But if you have the residual variances be the same, and you introduce random slopes related to time instead, it creates different values on the diagonal. So they're both trying to recreate whatever heterogeneity would have needed to be there. They're just doing it through different means. So that's what I mean by redundant, is that they're both trying to accomplish the same goal. And that may cause problems if you don't have a lot of occasions, especially. Okay, so V then is what I've got up here. What's V? Yeah, G plus R, right? Or G and R is the way I usually try to say it. Welcome to the jungle. We got candy, not just fun and games. Candy made its way back around again? We're all good on the candy? Okay, good deal. So V is 6 by 6 because G needs to get pre and post multiplied by one more letter. Z in this class, yep. And by the way, each paper you read, they're going to have their own letters. These letters go with the SAS documentation. That's where I've landed. Most commonly, otherwise, I will see T instead of G. And some people will do sigma instead of V. But that one actually makes sense. The T one just seems equally arbitrary. But you got to have at least some labeling system to go with here. But it's always author specific. Okay, so yeah. Confidence intervals. If I have 3 random effects, that means there's 3 different confidence intervals. And if I wanted to, this is foreshadowing next week, if I wanted to add predictors to this model, how many sources of individual differences do I have to explain? 3. That's what random effects are. They are sources of individual differences. There are 3 different ways that people differ from each other according to this model. That means how many potential R squares would I have? For person predictors. How many sources of individual differences? We said 3. So how many R squares for how much of those differences we have captured by the model do we have? 3. And there's actually a 4th. Residual variance is also still here. But people things cannot explain residual variance directly. Residual variance is why are you off your line today? Things that are constant to a person can't describe why this day is different than the next day. All right, so then we looked at all this different stuff. Here's a scorecard of sorts. Because at the end of the day, you can't just fit models for the rest of your life. You got to pick something, write it up, and turn it in, right? So by what standard should I pick something? We have a bunch of different possibilities. So from the polynomial models in example 6a, we ended up with random quadratic. How many individual difference sources are in that one? If I have a random quadratic time slope. That means I have random quadratic, and what's underneath it, hierarchically? Linear. And what's underneath that? Intercept. So 3 in that one. Piecewise, with both of the slopes being random, how many sources of individual difference is there? Also 3, 2 slopes and 1 intercept. Negative exponential. Now note the wording here. Random asymptote, so where you end up with individual differences. Random amount, how long it took to get there, individual differences. Fixed rate, which is how quickly you approach asymptote. So how many sources of individual differences? Just 2. Random linear log time, 2 sources. Random quadratic log time, 3. So the scorecard here is saying relative to saturated means, how well did whatever fixed effects are in these models recreate those predicted means? Well, the first model, not well enough. The others, all well enough. So from that perspective, anything but the first one would be acceptable. On the variances side, how well did these random effects recreate the what? How well did the random effect variances and covariances, along with the residual variance, recreate the what? It's individual differences would be one part of it, but what's the answer key? Unstructured, yeah. There could be individual differences in there, but they're not pulled out in an unstructured model. They're just letting everything be what it wants. Yep. So relative to unstructured, how well did this fit? And this we're looking for not worse, because unstructured is the best. So the first one, worse. Second one, not worse. These ones, worse. Third one, not worse. So I see a pattern here that is broken by one entry, but the other four follow it. The models that have 3 sources of individual differences appear adequate with respect to the variance side. The ones with only 2 don't. So I think that's diagnostic information. Here are comparisons, though. So in order to compare absolute fit, like for both sides at the same time, I had to switch to maximum likelihood. So I have the bolded values are the lowest values. So this is -2, which is an index of data shortness, not height. And ML, AIC, and BAC likes that one the best. So here is a chi-square log likelihood ratio test. There we go. Log likelihood difference. And it looks like the only 2 that fit are random quadratic log time and the piecewise model. So those would be the 2 that I would probably pick between. Do you have any preferences? What would you go with? Random quadratic log time or piecewise?
Should we pick up the most interpretable one?
That'd be the next thing. It's like, what do you want to write about?
Yeah.
Do you want to explain quadratic log time to your readers? Because I don't. Piecewise it is! Yay!
Yeah, I think it would depend on who my audience was. Like, if my audience was like mathy people who know a lot about it, maybe I would go with random quadratic, although I wouldn't want to write about it,
Yeah.
honestly.
Yes, if you were writing for an audience that had a more technical understanding to start from, then yes, you would be less concerned about overwhelming them potentially. That is always a good thing to keep in mind, interpretability and usability.
Or if you want to publish twice.
Yeah, or you write it up 2 different ways and send it to 2 different places, but no. There's a word for that, like salami slicing or something. Isn't there a phrase for that? Yeah, when you like cut up, or LPU is an abbreviation, least publishable unit. That's a thing. Not advisable. Yeah, it always depends. The answer to every question on earth is it depends. I think that at some point you need numbers of papers on your CV, and LPUs get you there. However, when you're going up for tenure and people that don't know you have to write about whether you've made an impact on the field and they can't think of a single important paper that's well cited, then that's great. So maybe some longer stuff that's more comprehensive that sort of plants your flag is a good way to balance the LPU publications. LPUs are good for grad projects, grad student projects. Like, here, you take this one thing I did and then you add this little piece to it, then that's your paper. Like, that's a reasonable way, I think, to proceed with that. All right, I have one more in here called latent basis, which we talked about a little bit. I thought it might be helpful, even if you haven't had SEM training, to just walk through how these models are conceptualized from that point of view. I've had questions over email about this as well. Would that be something you'd entertain me? Talk about how these models look in SEM a little bit? You're like, can I have more candy if I say yes? Certainly you can. So I wanted to go back actually to lecture 5, because I have a section in there that starts from like the empty model and builds up. The ones that are in this slide presentation are more complex. So one second here. It's thinking about it. Any questions while my PowerPoint is thinking about opening?
Can you give us a tiny baby little overview of what SEM actually is?
Yes. SEM is the same thing as multi-level modeling. Next. Here's the intersection. Random effects are latent variables. So everything that you think of as a multi-level model, like, is also a structural equation model at the same time. That's the connection. The idea of SEM is that it's a multivariate analysis technique. So predicting lots of things at the same time. And the things can have link functions and conditional distributions, so you can predict ordinal things or binary things or continuous things or count things and whatever you want. If you just have observed variables, so like if you have a multivariate regression where you got a bunch of predictors, a bunch of outcomes, you want to see how they're related, maybe throw some mediators in the middle. What's the other word for mediator? Collider, whatever. Yeah. I'm doing the mediation triangle with my hands. That's what this is. If you just want to do that, that's called path analysis or path models, and it's not different than just standard single-level regression, other than the fact that there's lots of them happening at the same time.
And a mediator is an interaction?
A mediator is not an interaction. You're thinking of moderator. Moderators are interactions. Moderators change the effect of a slope based on another variable. So they answer the question, does X predict Y? Well, it does in these people, but not in those people. Or it does in people who are high on this, but not on people who are low on this. It's like a conditioning. Mediator is like, my intervention is going to fix the parents, and because I fix the parents, they're going to fix the kids. It's like a causal type of idea, and you would need a design that supports that interpretation.
We can't do mediators in multi-level models?
You can do mediators in multi-level models, but you can't do them all at once in this type of software. So the problem is that, like in these examples, we have Y as one column. In a mediation model, X predicts M. M needs to turn around and become a predictor of Y. But there's only one column. And there are ways people have figured out to trick it into doing it, but then you can't look at mediation at level 2 and level 1 at the same time. So then if you want to add latent variables or random effects, latent variables are the idea that you have these observed outcomes, but none of them is like a perfect representation of the thing you want. So items on a test is the context that like SEM is usually thought about. And the latent variable then would be like this imaginary thing that causes you to answer the questions in the way that you did. And so all of your answers put together should essentially inform where you stand on this underlying thing. And I'm making circles because that's what it is. So the connection to longitudinal is that you have these latent variables for intercept and latent variables for how much you're going to change. And your items are your occasions. Okay, does that help? And then you can put arrows between your latent variables that are slopes or covariances. And you can set it all up to be as complicated as you'd like. So then, this is slide 44 of lecture 5. So we're going back. This is one of the videos that I posted while I was at a conference about a month ago. So the connection is that random effects are latent variables. So there's one other thing that we have to change to do this, and it's the data structure. SEM software uniformly uses what's known as a wide format data structure, where it's one row per person. And so you'd have a column for your score at occasion 1, your score at occasion 2, and so forth, all in one row. So you would have to unstack or restructure the long data that we have, where it's one row per outcome to do this. So a typical factor model would look like this in a measurement context. Each item response for each subject, and yes, I know that I is a wrong thing here, but I had to change it in that notation, is a function of an individual item's intercept, a factor score, which is the idea of this underlying thing, that's a subject variable, and then lambda here is a slope, it's a factor loading, that says how related this underlying variable is to this item response, and then E is error like usual. So the trick is to recognize that F's are U's, so what we would call factor scores, in SEM notation, we're calling U's as random effects. And the loading in front of it is estimated in SEM, but fixed time values as what we're going to do instead. So let me start with an empty model. So this is slide 46. Empty model, no random intercept. Like this is E only. Like this is the simplest model you could ever have for time, and then this I is for person. So I have my fixed intercept and my level 1 residual, but it's all the variance at this point into this one pile. So if I have 4 occasions as my 4 y's here, the lines going from the red circle down to the black outline boxes, these are factor loading slopes. That's because there is an implicit 1 here. That's what the 1's mean. And I have a latent variable that has only a mean and no variance in this analysis. Last but not least, the little e's down here are the idea of time-specific residuals. I am fixing their variance equal to each other to be consistent with our R matrix being diagonal with the same variance on each occasion. To add a random intercept then would be to add a variance for this latent variable. So the mean of the latent variable is the fixed effect. The variance around it is the variance of the random effect. And these are all 1's here, so this is all an intercept. And if you took IRT, this is now theta. This, if you have a Roche model where all the loadings are equal. That's why I say multi-level is everything. If you were to let these loadings differ, then it would be a different kind of model. It would be like a 2-parameter model or a traditional CFA model. If I wanted to add fixed time, I do that by adding a second latent factor. And there's a special thing here. Its mean is the fixed slope that goes with it, but note what the loadings are now fixed to. They are fixed to the time column that would go with this. They are not estimated. So by fixing the loadings into this pattern, I have reinforced what the meaning of this variable is going to be. This is a linear time slope specifically because of the pattern I've enforced here. If I fix the variance to 0, then this variable has a mean only. I can add then a random slope to go with it and estimate its variance. And then the 2-headed arrow in between here is the covariance. So this would be like the G matrix. Question?
How can you fix variance to 0?
In the software. So we've been doing that, but just not explicitly. By not estimating a random effect, you have fixed its variance to 0. But in SEM software, when you introduce one of these latent variable circles, it automatically assumes you want a mean and a variance for it. So you have to shut that off. So when you add it, you can add the covariance with it. So here's the big connector slide. The residuals down here, that's my R matrix. The random variables up here, random effect variables, that's my G matrix. The loading patterns down here, that's my Z matrix. In SEM notation, then we would have, let's see, Z is the lambda matrix, G is what, psi? Phi. I always get those two confused. I don't do SEM notation with the Greek letters very often. This is the error matrix, this is the factor matrix. How's that? That's good enough. And Z is the loadings. So this then brings up a potential problem. What about unbalanced time? What if somebody showed up at time 0, time 1.2, time 6, 2.4, and 3.9? And someone else showed up at different times. What am I going to fix my loadings to? 1, like with air quotes around it, 2. So you need a piece of an option within software that's known as a definition variable more generally. And what it would be is 4 columns that would say exactly when time 1 was, exactly when time 2 was for each person. And you would say, hey, can you take that first column and whatever value is in that data set, make it the loading for that person. And take the next column and make their loading whatever their value is for that occasion. So it's like individually specific factor loadings at that point. The only software I know of that does that I can use is M+. In R, there's OpenMX is a program that's now integrated with R that has this capacity as well, but Lavon does not, to the best of my knowledge. I'm not sure about Amos or other structural equation modeling programs. Does anyone know? Anyone use those? I don't think Stata does either in its SEM thing. I don't remember seeing that.
I haven't played around with SEM
Yeah.
to be confident, but it wouldn't surprise me if they did.
And then multi-level SEM is another thing, but we're going to leave that alone for today. That's enough. That's the advanced class. So then if you wanted to, this is slide 43, if you wanted to add quadratic, this is too small. Right. There we go. Do you see the loadings? So this would be for our example with the 6 occasions. So this is a linear slope because I have fixed the loadings to a pattern that implies linear change. This is a quadratic slope because this is time squared. The intercept is an implicit 1. So time multiplies beta 1, time squared multiplies beta 2. Essentially what I would have right here is like a variable that's a constant to make the pattern the same, and that's why these loadings are all, come back mouse, lost it. Come back. It's like a ghost mouse. It's like making things move, but I can't see the cursor. Freaky. I know. Okay. Do you see that? I'm not losing my mind. I might be, actually. Take that back. My mouse has lost its mind. Okay, stop it. There. Hey, what's that? Apparently I just don't get to use my slides anymore. It's fine. I'll make it work. So how would I do like a piecewise model? That's the one we decided we like best, right? Can I?
Differentiating between the load-ins.
Yep. I can use my hands. There. Sorry, Zoomers, my mouse has died. I'm pointing at things. Change the loadings. So yeah, if I wanted the first latent variable to be slope 1, 2, that would be like 0, 1, 1, 1, 1, 1. The second latent variable, if I wanted that to be slope 2, 6, 0, 0, 1, 2, 3, 4. So you can make whatever patterns you want to. Okay. This is really funny. I can't get over to the thing. I keep hitting like escape and I'm like, why? What am I doing that's wrong here? 1 second. Let me stop the screen share so I can get this fixed or I'm going to lose my mind. Okay, apparently I can't. And now I can't get the screen share going again. Oh, the mouse on here works. Okay, trackpad for the rescue. Now I can get the screen share going, but I don't know if I can get over to the thing. All right, fine.
It's Windows D,
Get back.
so is it showing anywhere?
Okay, thank you. Now let me get to the slideshow. Thank God. Thank you.
What was that? He's just sitting on that and watching you suffer.
Seriously. No more candy for you. There. It fixed. I don't know what I did, but it's fixed. Okay. But what I wanted was the other one. I wanted this one. So this is the one we were at with the quadratics. So the latent basis idea then. That looks like this. Let me zoom in so that you can see the loadings a little better. This is just change. What kind of change? I don't know. You figure it out. So I have to nail down 2 of these for identification purposes. And I've chosen 0 for the first occasion and 1 for the last. Another reasonable choice might be 5 for the last so that the change is then the same metric as all the other models. But this one theoretically allows us to see how much change has happened proportionately by each occasion. And so it estimates these essentially like their time occasions. Like to make this change pattern, what would be the time coding that would make it? And it figures out what kind of nonlinear change you have. So I did fit this model. And I think I wrote down what the loadings were. Yep, I did. So here's code that won't make any sense to you because it's M+ code. But for those of you who've seen it before, it will look familiar. The loadings that I ended up with were these numbers right here. So this is telling me most of the change is happening over the first 3 occasions, and then not much is happening after that. However, the comparison table said that this one fit significantly worse. And I think part of the reason is because there's only two sources of individual differences and not 3. That's my hypothesis. It looks like these data want 3. Question?
So for the previous slide,
The quadratics?
So are
Yep.
we assuming how to differentiate between the latent variable, linear time, and quadratic time?
Yeah, they're 2 different things.
So, so we are assuming that they are latent. There is no formulations for that. I mean formula. So another way, how do we fit like the exponential, negative exponential model here? Or
Exponential models, what you have to do is constrain the loadings to be whatever would be created by that function. So-
we do the transformation with the loading.
Yeah, let me see if I can find it real quick. Again, leftovers, I tried to warn you, right? Because I know I've done this. Here, go over there. That's me. That's my book. This is the book's website. Every model in the book is in here in at least 3 of the programs, if not all of them. It's chapter 6, M plus is this one. Negative exponential models are down here, so we'll do like that one. So what I did was constrain, essentially estimate the variances over time and that one, and then constrain what the means are to be consistent with the model,
Oh, okay.
like that. And so then I built the rest of the parameters out of that as well. And it worked for some models, but not all of them. So then this one actually did converge. So you can see that later if you'd like.
Thank you.
Sure. Yeah. So I have M plus syntax for these models. Here's a quadratic and latent basis, and then I have Lavon syntax for the same thing, so you can take those. So I know class is about over, but I want to tell you a quick story. So a former student of mine was planning their dissertation, and he's like, I don't know, I have this longitudinal data, 4 or 5 occasions. I don't know if I should do multi-level modeling or I should do latent growth curve modeling. What do you think I said? Yes, yes, you should. So I start digging into his question, like, well, how would you decide which way to go with this? Number 1, what's your sample size? If he tells me he has 30 people, he needs to stay in Rimmel land. But he had like 300. Great, okay, so you can choose either one. Do you have balanced time? Next question. Because if you have unbalanced time, then you need software that allows you to have the individually varying factor loadings, and that can be tougher to come by. By the way, when you have individually varying factor loadings, all of your measures of absolute fit and SEM go away. They're gone. So you won't know if your model doesn't fit. Yeah, that could be used for nefarious purposes, actually. You could pretend like you have unbalanced time and be like, I think my model fits just fine, I don't know. Those are my 2 questions then. Number 3, I should say, do you have observed outcomes or latent outcomes? Because each of these boxes doesn't have to be a box. What if I have a latent variable measuring my outcomes at each occasion, and I want to turn this into a circle? Could I do that?
Is that what makes it a mediator?
It wouldn't be a mediator necessarily. This would then be called a second order growth model, because then you have your intercepts and slopes up here. They are predicting your latent variables per occasion as the lower level, and then below that would be your observed indicators of the latent variables at each occasion. So if he wanted to do something like that, he needs to shop at the SEM store for his model and not the MLM store. What if the children are nested? What if they're nested in classrooms or schools? And he wants to shop at the SEM store.
Add more level.
I got to add a level. But then you got to shop at the SEM store that has that capacity. because we're talking about multi-level structural equation modeling at that point. Do you want to do mediation? That would be another question. That you need to buy that at the SEM store too, most likely. There are ways to do like separate regression type things, like the classic, what is it, Barron and Kenny, that classic paper. They're the ones who introduced the way of doing mediation where it's like you do this regression and then you do this regression and then you do this regression and then you put it all together with math. Well, you can do the same thing with multi-level models if you have to. It's just less than ideal, I think. Can you think of anything else I should ask him to decide whether he would do multi-level or SEM for his longitudinal models? That was about the end of my list, but those were the things that I would think about.
Can you summarize again? So if your sample size is small, you would do multi-level?
If your sample size is small, then you need REML estimation, which is only a thing in multi-level software.
Okay.
It is not a thing in SEM software, although it very well could be.
Okay. And then if you have unbalanced data, you should also use multi-level.
If you have unbalanced data, you either need to use a SEM software package that allows individually varying loadings to address the unbalance, or you need to go to the multi-level store instead.
Okay.
Okay, questions back here? No? Okay.
Yeah, what about the outcomes? What happens if that's not continuous?
If
Is
the
there any
outcome,
advantage in SEM compared to UniVTML?
so the question is, what if you have a non-normal outcome? Do you think you can fit multi-level models to like count data or binary data or ordinal data? You cannot? Are you sure?
Yes, you can.
Yes, you can. It's hard, but one can do it. So then the question would be, what do you have? Does your SEM package have the right link function that you need? So for instance, M+ has the most link functions of any SEM package I'm familiar with. It has the counts family and ordinal, nominal, and binary. It doesn't have anything for binomial. So if I'm modeling change in proportion over time and I'm concerned about keeping the proportions bounded between 0 and 1, can't do that in M+ very easily. Then I would want to go to software that has proportions built in for link functions and distributions. So yeah, that could become a concern. Other things you can think of.
Is it only one output or more than one output?
Oh, one outcome or multiple outcomes. That's a great one. So one of his questions was, we're going to measure change in this thing, and change in this thing is going to predict change in that thing.
That's SEM.
That's SEM. Yeah, you need a multivariate model at that point. It is possible to trick like Elmer into doing that, but then you only get covariances. You can have like this, you just basically have a giant G matrix that has a bunch of covariances in it for both outcomes at the same time. But if you want to have predictive relationships or moderation thereof, you can't do that in standard multi-level software. So yep, that would be another reason. There's lots. So these connections I hope to delve into a lot more in the spring class. I am kind of assuming you've had some SEM if you come to that, by the way. So if you haven't, it might be better to wait a little bit, or if you're willing to do a little studying on your own. The SEM class I taught last year is still up, of course, on the YouTube, so just a little bit of that, like the CFA part of it, would be enough. Question?
Back to the story. So is the causal story affecting that? So if the researcher believes that there is like a latent variables affecting the results, so you should go to the SEM instead of the multi-level modeling, or you still can use multi-level modeling with latent variables?
So with latent variables depends on whether you're thinking of just the intercept and slope as the potential latent variables for time, or you're talking about predicting latent variables as outcomes.
Predicting latent variables as outcomes.
Predicting latent variables as outcomes is the SEM store. Technically, you could force NL mixed or something like that to do it. It's not worth the hassle. Yes, and you would think that latent growth curve modeling would be that. Studying growth curve modeling of latent things? No, that's not what that means. Latent growth curve modeling is what I'm teaching you using MLM software. It's second order factor models is what you would call that, or growth of factors, factor of growth of curves, that kind of thing.
But all are observed.
In this class, everything's observed.
Yeah.
Yep. Can't do everything at once, but we can do all the pieces. Okay, other questions? Should we call it a week? It's been a long week. I think we deserve 6 extra minutes of your life back or whatever it is. So formative assessment due Monday, homework due the Monday after that. Please let us know if you need anything. Thanks for being here. Have good weekends. Grab some candy on the way out.